Mr. Chairman. So my name is Mir Rashid Mualim from the Department of Material Science and Engineering at the Technion, and my supervisor, Professor Dov Sherman, from the School of Mechanical Engineering at Tel Aviv University. I will talk about the effect of reflective stress wave on correct speed in quasi-statically loaded brittle crystal specimens. I will start with a short introduction. A Freund equation of motion describes the energy-speed relationship of a propagating crack in a half-infinite isotropic and elastic body using continuum velocity dynamics, where atomistic considerations were not taken into account, and therefore this is considered as the upper bound of the energy-speed relationship. And according to this energy-speed relationship, the crack speed normalized by CR, where CR is the really free surface wave speed, and it is the upper limit of the crack speed in the material, is equal to 1 minus gamma, where gamma is the cleavage energy, and according to Griffith criterion, it is equal to 2 gamma S for ideal brittle crystals, where gamma S is the relative free surface energy, and it is the resistive force for crack initiation and propagation, divided by G naught, where G naught is the static energy release rate, and it's a function of the geometry, the loading conditions, the material properties, but for a stationary crack, and it is the energy supply to the crack tip. It is worth noting that the Freund equation of motion do not take into account the effect of reflective stress wave from the specimen boundaries. So we postulate if we build the energy-speed relationship from our experiments and we compare it to Freund equation of motion, each deviation should point on an energy dissipative mechanism that could be the effect of reflective stress wave on the crack speed. I would also like to share with you my last results on the rate-dependent cleavage energy. So our assembly consists of an aluminum molding frame with a rectangular hole at the middle, to which we glue a rectangular pre-cracked silicon sample here with these dimensions, and we propagate the crack at the low cleavage energy system 110, 1 minus 10. We glue the specimen using a 50 micron thick epoxy resin at each side of the specimen, and we keep the whole assembly in a temperature chamber for 4 days to ensure that the epoxy is fully cured. After the curing process, we heat the whole assembly on top of an electrical heating stage at a slow rate to ensure advanced static loading. The driving force for crack initiation and propagation is the coefficient of thermal expansion mismatch between the aluminum and the silicon, where the coefficient of thermal expansion of aluminum is 1 order higher than that of silicon. So when we heat the whole assembly, the aluminum expands more than silicon, and the pre-crack propagates. To calibrate our system using finite element analysis, we have to measure the strains and the temperature on the sample and the temperature on the frame. And the big advantage of this assembly is the ability to control the energy flow to the crack tip and hence to propagate slow cracks or high-speed cracks. To propagate high-speed cracks, we had to measure several parameters in this assembly that were determined using finite element analysis. This is our 3D model in Abacus, and in this curve we can see the change in the quasi-static energy release rate as a function of the crack length. And this is an example of the pre-crack how the pre-crack affects the energy of the crack. So if we look at the red curve and we want to propagate a crack at the 2 gamma, we can propagate a long pre-crack. But to propagate a shorter pre-crack, we have to supply more energy to the crack tip, and hence we have to supply more driving force, which is in our assembly more delta T, and the crack will propagate according to the blue curve and will reach a higher energy regime. It is worth noting that the rate of energy flow to the crack tip during the crack advance for short pre-crack is higher than for long pre-crack. And the other 2 parameters that we have to determine are related to the epoxy, where we found that to ensure a good energy transfer from the aluminum to the silicon, we have to use a thin epoxy layer with high effective elastic modulus of elasticity. To build the energy-speed relationship, we have to measure the crack speed during crack propagation. This was done using 2 different techniques. The first is the potential trap technique, in which we deposited a 20 nanometer titanium conductive layer on the crack path. And when the crack propagates, it cuts the aluminum, the titanium conductive layer, which it performs as a variable resistor, and the resistivity increases. And hence, the voltage change as a function of time, and to translate the voltage to crack length, we use a calibration process which gives out the voltage as a function of the crack length, and after several manipulations between these two curves we get the crack length as a function of time, and the derivative gives us the crack speed. The second method is the Wallner lines, which are lines that are formed on the crack fracture surface as a result of an interaction between the crack front and the reflected shear stress wave from the free surfaces of the specimen. And the inclination angle between the crack front and the primary Wallner enables us to calculate the crack speed. This is an example of the speed as a function of the crack length that we get from our experiments. The red and blue curve are represents the speed that was calculated using the potential drop technique using high resolution scope and low resolution scope, and the black dots represent the speed calculated using Wallner lines. We can see a great agreement between the three results, and that points on the reliability of our results. And to examine the effect of a reflected stress wave on the crack speed, we had to ensure that the energy is reflected back from the epoxy resin. To calculate the energy that is back from the epoxy resin, we performed a dynamic finite element analysis, in which we took a cross-section of our assembly, where at the bottom there is the silicon sample, relatively there is the epoxy, and at the top there is the aluminum molding frame. To simulate a propagating wave, we applied short duration pulse to the silicon sample, and you have seen that the wave propagates in the silicon until it reaches the epoxy resin, where part of it is reflected back to the silicon and part of it is transmitted to the aluminum molding frame. And according to these simulations, we can see in this curve the silicon energy as a function of time. This is the impact pulse, and this is the reflected energy from the epoxy. According to this curve, 76% is reflected back to the silicon, and this is in a great agreement with the analytically calculated value using the acoustic impedance of the silicon and epoxy. And it is worth noting that this equation do not take into account the thickness of the epoxy and do not consider the aluminum molding frame. As I have mentioned before, if we build the energy-speed relationship and compare it to Freund equation of motion, each deviation should point on an energy dissipative mechanism. In this curve, we can see that the blue curve represents the Freund equation of motion, and the red curve represents our results. Since in our assembly, at the end there is an edge effect, the energy decreases, but we postulate that if the specimen is longer enough, this curve should continue at the same course. We can see that there is a deviation from Freund equation of motion. To check if this deviation is as a result of the interaction between the crack front and the reflected stress wave, we calculated the time that it takes the wave to travel to the epoxy resin and be reflected back to the crack tip. This was done knowing the speed of the wave in the material and the distance that the wave traveled from the crack tip to the epoxy and back to the crack tip. And if we land these results on this curve, we can see that just the shear stress wave affect the crack speed, and this effect is very weak, where this decrease in the speed is about 5%. The other important result from this curve is that when we try to find the best fit of our results to Freund equation of motion, we had to use gamma of 4.1 joule per meter square, which is about 30% higher than the 2 gamma S of this cleavage system, which is equal to 3.5 joule per meter square. We also found that when the rate of energy flow to the crack, the burn to crack advance is high, the energy that needed to break the bond is higher, and it reaches the steady state more quickly. Trying to understand this behavior, we try to look on the crack propagation mechanism. And in this image, optical image, we can see that the water pre-crack is curved, and this indicates that the crack propagation is via atomistic steps, which is called double kinking. And the energy barrier for double kink formation is higher than the energy barrier for the double kink advance. So we postulate that at high energy rate of energy flow to the crack tip, it is the double kink is more likely to be formed, and when it is formed, it will propagate until it reaches the specimen edges, because the energy barrier for the double kink advance at high energy is relatively low. So at high speeds, the crack front, we postulate that the crack front is straight. We have some evidence from Walnut lines where we can see that for fast cracks, the crack front, which is the yellow line, is straight. That indicates that the crack front is straight for fast cracks, while for slower cracks, the crack front is not straight and has an inclination angle that is called beta, which is higher than A0. So I will summarize. We have performed high-speed cleavage experiments using the CTEM method for quasi-static loading of brittle crystals. We show a good agreement between speed measured using the potential graph technique and Walnut lines. We show that Freund equation of motion well predicts the energy-speed relationship for brittle crystals for after crack stability, and that the reflected stress wave only weakly affect crack speed. The crack propagation mechanism is via double kinking, advance, and formation. And as the energy flow rate increases, more energy is required to break the bond.
Okay, thank you very much, and for your time.